So now we shall discuss what is known as the Deutsch problem. The Deutsch problem will be defined, so do not worry. So this will be a sneak peek into what a quantum algorithm might look like. Not might look like, what a quantum algorithm looks like. So rather than talk about one of the conventional algorithms that you can find in any of the material or textbooks that you can, that is available. We are talking about a simpler problem which is also available in the same textbooks, but not discussed as often. The reason why we are discussing this particular problem is that it is very simple, and therefore it will be much more easier to explain and follow the progress of follow the computation that is being performed through this throughout this algorithm, and that will essentially highlight the key features of quantum computation that we wish to emphasize on. Now, we could have picked up, I don't know, maybe something like a more famous Grover's algorithm or the Shor's algorithm, but the problem is the mathematics in it is so dense that we will mostly get sidetracked in explaining the mathematics, and the actual quantum features that we would like to highlight will be lost. So for that process, we are, for those reasons, we are we shall be discussing about the very simple Deutsch problem. Even classically, it's a very easily solvable problem. Yeah, so these are the split of topics. So let us go back to Boolean functions for a second. So as defined before in yesterday's lectures, an n-bit Boolean function takes in an n-bit Boolean string as an input and gives an output f of x. So the input can have 2 to the power n possible values going from all zeros to all 1. And the output can have one of 2 possible values, 0 or 1. Now a Boolean function can be called constant if all the outputs corresponding to every input string is either 0 or 1. So if f of x is equal to 0 for all x belonging to 0, 1 to the power n, then it is a constant function, or if it is 1, it is also a constant function. So these are the only 2 constant functions that exist for any n-bit Boolean function. For a 1-bit Boolean function, these are the only 2 constant functions. For a 2-bit Boolean function, these are the only 2 constant functions, and so on. Now we are defining another variety of Boolean functions that is known as a balanced Boolean function. Now what is a balanced Boolean function? It is when the outputs 0 and 1 occur an equal number of times. So what does that mean? So since I have 2 power n possible values for the inputs, I will get 2 to the power n outputs. Now in this, I need to have zeros and ones occurring an equal number of times. So therefore, if I have 2 to the power n inputs, then the output 0 will occur 2 to the power n divided by 2, that corresponds to 2 to the power n minus 1 times, and 1 will occur the remaining 2 to the power n minus 1 times. Is there an example for such an operator? Yes, the 2-bit XOR operation is a balanced function, is a balanced Boolean function. As you can see, when both x0 and x1 are equal, the result is 0. Therefore, 0 plus 0 and 1 plus 1 is 0. 1 plus 0 and 0 plus 1 is 1. Therefore, 0 and 1 both occur 2 to the power 2 by 2, that is 2 times. So that is a balanced function. The single bit NOT operation is also a balanced function. These are examples, 2 elementary examples. But however, it should be noted that all Boolean functions cannot be classified to these 2 types only. There can be functions that are neither constant nor balanced. In fact, as we look at larger and larger Boolean functions where this n keeps growing, these functions become more and more common. So a simple example for a function that is neither balanced nor constant is the 2-bit AND gate, where the outputs are 0, 0, 0, and 1. So in that case, of course, 0 occurs thrice and 1 occurs just 1 time. Therefore, it is not constant. And since number of times it's occurring is not equal, therefore it is not balanced. Now, yeah, I just mentioned that we shall not talk about classical oracles, and this slide is titled Classical Boolean Oracles. What do I mean here? Well, let me go through it, go through this slide, and you'll understand. So what is a classical oracle? What is it the thing that I'm referring to as a classical oracle? It is, again, a classical system that will take an input value x and give me an output value f of x. So it is perfectly possible to implement this. Now, why do I say this? Okay, yeah. So such an implementation is known as a black box implementation when the form of f of x is not revealed. So what we can do is only give a value of input and see what the output is. We don't know what the function is, therefore we cannot guess what the value is going to be. So all we can do is give an input, expect an output. Now this is nothing special in the case of classical computation, because if we have if you have implemented a Boolean function on, say, a programming language like C, then the output file that we generate from it has no, I mean, technically it does have the information of what is the function, but it is not possible for us to extract that information. So the output file will take an input and give us the output. So that is actually a classical black box oracle. So classical black box oracles are actually very common. So they are not anything special. So now we are coming to the Deutsch problem. So what is the Deutsch problem? The Deutsch problem is simply this. If we are given a black box oracle, classical or quantum. Okay, for now, we shall not talk about the quantum part. We shall stick to the classical part. We are given a classical black box oracle. Therefore, I can essentially input a certain value and the oracle will evaluate and give me what the output is. So if I'm given such an oracle and I'm guaranteed, as mentioned here, it is assured that the given oracle definitely represents either constant or balanced functions. So I'm guaranteeing that the oracle that that I'm presented with is either balanced or constant. So now my aim is to guess if it is constant or balanced. Again, I only want to know if it is constant or balanced. I don't want to know what the exact form of the function is. So the Deutsch problem only asks, given a black box oracle, is it possible to find out if it is constant or balanced? Now, obviously, at this point, people can stop and ask, what is a black box oracle? I mean, since even to build that black box oracle, I need to know what the function is. So why does this problem even make sense? So in a realistic scenario in our world, we can think of it this way. So let us have a very large Boolean function. Say, a Boolean function that acts on, say, something like 200 variables, 300 variables, that has a very definite expression. Now, even if I were to give that expression to a person, they will not be able to calculate the values, or they will not be able to guess all possible outcomes of that function, because we do not have that much computing capability as human beings. Therefore, for very large Boolean functions, a black box oracle is the only oracle we have. And since it is a very large Boolean function, it is also not very easy for us to guess if the function is going to be constant or balanced. Therefore, this approach that is described in the Deutsch problem will be adopted even for very realistic Boolean functions. Now, if you want to ask me where will I find Boolean functions that act on 200 or 100 or 200 classical bits, the answer to that is very simple. I mean, they're present everywhere. The most common example would be something like a hash function. So have we come across a hash function? Yes. Programming assignment 1 involved you entering the answers of your question to one of your blocks in the Python code, which generated a string. So that was a hash. So that actually featured a Boolean function that had a very large number of variables. The output that you got is essentially a hexadecimal output. So it can be converted to a Boolean output. So the length of that string is roughly the size of your Boolean function. So such functions are very commonly present, and therefore, whether such functions are balanced or constant, or analyzing the nature of such functions, is something that we do in real life in several fields, most notably in cryptography. So the classical approach. Now, given this oracle, what can we do? The only thing we can do is give it an input and see what the output is. So that is all we are going to do. So this act is called querying. This process is called querying. So if we can only give an input and ask for an output, then okay, fine, I will give some randomly chosen input. I will see what the output is. Then I will give it a different input and see what the output is. Now, if these two outputs differ right away, then I can say that my function is definitely not constant, because a constant function, I mean, by its definition, is constant. So, and since I'm assured, I'm guaranteed that the oracle that is presented to me is either constant or balanced, the moment I see a varying output For the first time, I can conclude that my function is balanced. However, if I keep getting the same output again and again and again, how many times do I have to query this oracle to find out if the given oracle is constant or balanced? So the trivial answer is I can give all 2 to the power n possible inputs, and if I get the same output 2 to the power n times, my function is balanced. But that is a lot of, can we find the same answer with lesser number of queries? The answer to that is simple. If my function is balanced, then the output 0 or 1 can occur only for a total of 2 to the power n minus 1 times, as we saw before. Therefore, if while querying my oracle, if I get 0 or 1 for even one more time, once more than 2 to the power n minus 1, then it means that my function is not balanced. Therefore, it has to be constant. So worst case scenario, if you have really bad luck, then for every query you enter, you're possibly getting the same output. But after you've performed 2 to the power n minus 1 queries, the next query will tell you definitively whether or not your function is constant or balanced. Therefore, by querying the classical black box oracle for a maximum of 2 to the power n minus 1 plus 1 times, it is possible to determine if that oracle is constant or balanced. Now, as the size of the Boolean function n keeps growing, we can see that this number keeps growing exponentially. Therefore, this particular problem has an exponential time complexity in terms of the classical solution. So this is a relatively complicated problem to solve using a classical computer. Of course, for smaller Boolean functions, the search is rather simple. But as I said before, if the function has 100 variables, then this task becomes very complex, because 2 to the power 100 minus 1, 2 to the power 99 plus 1 is actually a very large number. So now we are taking a very limited category of the general Deutsch problem. So now we are restricting ourselves. So this is the proper definition of the Deutsch problem. The problem that we referred to previously is the Deutsch-Josa problem. But okay, so now we arrive to what is precisely known as the Deutsch problem. What is the Deutsch problem? We have a Boolean oracle that represents any one of these 4 single variable Boolean function. So we do not know which one of the oracles it is. So now we are supposed to find out if the function is constant or balanced. How do we do this? We have to perform, as seen here, 2 to the power n minus 1 plus 1 queries. This is a single variable Boolean function, therefore n equal to 1. Therefore, we'll have to perform 2 to the power 1 minus 1, which is 2 to the power 0, which is 1, plus 1, 2 queries on the classical oracle. So by querying the classical oracle twice, we will find out if the function is constant or balanced. Now, this answer can be seen very intuitively. The classical function has only 2 possible inputs. So I will query it twice for both those inputs. If they are the same, then the function is constant. If they are not the same, then one has to be 0 and the other has to be 1 in whichever order, and therefore the function is balanced. As you can notice, these are the only 4 Boolean functions present. And if you can look back at the truth tables that was defined by Abhishek in his workbook, then you'll see that these 2 are constant functions, and f of x is equal to x and f of x equal to x bar, which is the classical NOT gate, are both balanced operations. So single bit Boolean functions are either constant or balanced. So in this case, mentioning whether a function is constant or balanced will tell us exactly what that function is for the case of the single variable Deutsch problem. So now we shall consider this quantum. We shall consider what we call the quantum solution and see what is going to happen here. So this is the quantum circuit. The highlighted region refers to my single qubit Boolean function oracle, which is why the bundle has been replaced by a single wire. There is a target qubit. So this will be one of the 4 oracles that I had shown in my previous slides. So that is why I've represented it as a generalized unit. Now we do not know which of this is present here. So this is given to us. We are free to choose the transformations we apply on this side and this side. This is given to us beforehand and we do not know what it is. So how do we find out what, I mean, we don't have to find out exactly what UF is. We want to find out if UF corresponds to a constant Boolean function or a balanced Boolean function. So this is the order of the transformations that are being performed. I'm starting with the initial state 0, 0. The big endian notation is adapted here, which means when I say ket 0, 0, I mean this qubit first and this qubit second. So now let us evaluate the algorithm stage by stage. Now you can ask, why have I marked a separate vector ket psi over here? It will become apparent towards the end. So now at stage S1, the transformation H, tensor H, is applied to the initial state 0, 0. So now we'll use a slightly looser notation rather than denoting it by a transformation acting on the state. I will simply say this state is taken to this state through this transformation. So now I'm writing it more like chemical reactions. And this is also a notation people adopt. This is something you'll find in virtually every textbook. So from now on, this is what we mean. This is the initial state, this is the final state, and this is the transformation that is affecting, this is the transformation that is affecting that change. So when I apply Hadamard, tensor Hadamard on 0, 0, each of the individual qubits will transform to the plus state. So I will have plus and plus. So I shall be writing the answers directly because we've been doing this course for around 3 weeks now, and sorry, 2 weeks now. And by now, the effect of these single qubit gates on the computational basis vectors should be known to all of us. So then at S2, the transformation I tensor Z is applied. As you can see, no transformation is applied to the first qubit. The Z gate is applied to the second qubit. The state that is coming in, however, is the state over here, and that is plus plus. So when the Z gate acts on the second qubit, we know that the plus state goes to the minus state. So the vector here becomes plus minus. Now, as you can see, this goes to the target qubit. From here, we enter the oracle. And since the minus state is being passed to the oracle, as we have seen before, we can now use the phase oracle notation. So when UF is applied to this state, then we know that we'll get a phase factor. But however, notice that my input state is now in a superposition. When I defined my, let me quickly show you the, no, yeah, let me quickly show you the, yeah. So when we were talking about the phase oracle, this was a single computational basis state. This was for the 1 qubit state, 1 qubit system, this would either be 0 or be 1. However, in this case, this is in a linear combination and the minus state is here. Therefore, now I use the linearity property. The input states are now 0 minus plus 1 minus. I've factored out the minus and written it as 1 by root 2, 0 plus 1 minus. So when UF acts on this state, what do I get? The minus state remains the same, but I get a phase factor. What is the phase factor? Minus 1 to the power fx. This is the value of x, 0 and 1. So here I will get a phase factor minus 1 to the power f0. And here I will get a phase factor minus 1 to the power f1. This is why I did not neglect the phase factors before, because right now I cannot always remove this as a global phase factor. When f0 is equal to f1, then of course the total thing can be neglected as one global phase factor. However, when f0 is not equal to f1, one of these will be plus 1 and the other one will be minus 1. So that is why when we represent actions for any unitary transformation, we do not get rid of the phases. When we apply it to a state, we replace the individual basis vectors present in the state with the actions, and then we will see if we can remove a combined global phase out to get the final resultant state. So this is why I did not neglect the phases in my phase oracle implementation. So finally, we apply a Hadamard transformation on the first qubit. So the transformation that is applied is H tensor I. Now, note here that this is minus 1 to the power f0 plus minus 1 to the power f1. If f0 is equal to f1, then it is minus ket0 minus ket1. I can pull the minus out entirely and get rid of it. And I will see that the resultant state when f0 is equal to f1. If both of these are 0, then it will stay as 0 plus 1. If both of these are minus, I will both of these are 1. I will get a overall phase factor of minus, which I can neglect. So in the case where f0 equal to f1, I don't know what that value is. In the case they are equal, the resultant state is plus minus. And when I apply the Hadamard gate on the first qubit, in that case, I will get back my 0 state and the minus state stays as it is because no transformation is performed. However, when f0 is not equal to f1, I will have a relative difference. If this is plus 1, this will be minus 1. If this is plus 1, this will be minus 1. In that case, I can pull out an appropriate phase factor and define it as the minus state. If you can, if you remember, this was also a pretty hotly contested question that was asked in the first quiz. So that this is the reason why this was featured in the quiz. So even though for an initial state we might get the minus of minus state, that global phase is neglected here. So the resultant state when f0 is not equal to f1 is minus minus. In that case, the first qubit becomes 1, the second qubit still stays in the state minus. That is why I marked the state ket psi here. If f0 is equal to f1, then the function obviously is a constant because these are the only two possible inputs for a single qubit state. And the state psi will be ket0. However, if f0 is not equal to f1, then the state psi will be in ket1. So now by simply measuring this qubit with respect to the computational basis only once, I can tell whether my function is constant or balanced. So when I get the outcome 0, my function is constant, where the oracle represents a constant function. When I get 1, the oracle represents a balanced function. So this is the Deutsch problem. This is the Deutsch algorithm evaluated in stages. So this was extended to solve this general problem where we have a general n-bit Boolean function. So that is the now well-known Deutsch-Josa algorithm. So Josa extended the reasoning, and what was found out, I will simply state the conclusion. I think Abhishek will have some kind of an implementation or a demonstration for the same. So you shall see then how the Deutsch-Josa algorithm works. But what Deutsch-Josa algorithm shows us is that even for the case where we have n-bit Boolean functions, the answer of whether the given oracle is constant or balanced can be found out by performing just one measurement. So that is the power of the quantum Deutsch-Josa algorithm. Whereas, as we can see, in case of the classical algorithm, we need 2 to the power n minus 1 plus 1 measurements, queries. Whereas in the case of the quantum Deutsch-Josa algorithm, as will be shown to you, the same circuit there, the UF will be replaced by the n qubit equivalent, and similar transformations will be applied. Abhishek will shed more light on what those transformations are. By just performing those sets of transformations once, we can say definitively if the function given oracle is corresponding to a constant function or a balanced function. So as you can see, even for this very simple problem, the quantum algorithm is performing faster than the classical algorithm. For the classical black box oracle that we would have received, we had to perform 2 queries. Whereas here we perform only 1 measurement. We perform all these transformations exactly once, and we perform 1 measurement, and that will definitively tell us whether the function was constant or balanced, which was the original aim of the problem. So with this, we arrive at the end of our current discussion. So I suppose I can take questions for another 5 minutes maybe.
Yeah, chat has been enabled. Please type your questions out in chat.
Oh, yeah, we also have to give them a break of sorts. So let me make it 10 minutes. Oh, oops. You sure? Yeah, I suppose the clock is visible now.
Yeah.
Yeah, it's visible, right? Yeah. So, yes. Can I please explain the Deutsch algorithm from stage 3 onwards? Okay. Was there anything? Practical use of this algorithm. Uh, Actually, the practical use of this algorithm is somewhat limited because the need to know constant and balanced functions is not particularly strong. However, this algorithm illustrates the fact that quantum computation provides a kind of speed up with respect to classical computation. So this was the proof of concept for quantum computation. This algorithm was the original proof of concept for quantum computation. However, the series of transformations that are being applied here can be modified and used for several other algorithms. So if you know the names if you know some named algorithms, you might come across what is known as the Bernstein-Vazirani algorithm. That is essentially the same as the Deutsch-Josa algorithm, and that has very important applications in terms of linearity testing of Boolean functions. Uh, Further modified versions can also be used. We at our group here used what was essentially based on this particular implementation of Boolean oracles and transformations to develop our own algorithm for linearity testing. And we have that algorithm. That algorithm has been published recently in a journal. So we have our own quantum algorithm. So yeah, Deutsch algorithm from step 3 onwards. I'll do that once I go through the other questions. Um, Quantum computation is faster only in certain problems like these, right? Not for every problems. Yes, definitely true. Only for a certain class of problems, and the comparison for that needs to be like, it basically depends on what kind of a problem we have and how it can be implemented on quantum computer. Not only it I mean it not only depends on what kind of a problem we are considering, it also depends on what kind of an implementation on the quantum circuits we are considering. So we can have one implementation that is faster than the classical version, and we can also make another implementation that is definitively slower than the classical version. So yes, quantum computation is not universally faster than classical computation. And once again, I emphasize, when we talk about quantum computation here, okay, yeah, this was actually, I have not made this statement before. Okay, so when we discuss complexities in case of quantum algorithms, we have to talk about two different kinds of complexities. As you know, one aspect is how long does it take to perform an operation. But as we know, quantum circuits do not give the same result upon measurement. It is always possible that I have a state that is a superposition of my basis vectors. Therefore, I will have to perform many such measurements. So quantum algorithms have, like the complexity of quantum algorithms has two dimensions. 1 second. Yeah, so I'm disabling the chat now so that we can also have a short break. So yeah, where was I? Yes. So complexity in the case of quantum algorithms is in two parts. One is the actual time required to perform the unitary transformation that we are considering, and also the number of measurements we have to perform to get a meaningful result. So that is known as the query complexity of a classical algorithm, and the time required to run it is the time complexity of the classical algorithm. The time complexity is measured in terms of the number of gates that we are using. The query complexity has to be evaluated by performing the experiment several times and finding out after how many measurements we are getting a definitive answer. So actually comparing classical computation and quantum computation side by side like that is not properly defined. It is not well defined. When I say that the Deutsch-Josa algorithm is faster than the classical version, I mean that whatever computation I'm performing several number of times in the classical computer, the analogous computation I'm performing only once on a classical computer. So that is essentially the speed up that I'm referring to. In this case, the speed up is in terms of the query complexity. However, we will have to pay attention to the actual time required to implement the quantum transformation also, to definitively say if a quantum algorithm is faster than a classical algorithm. So on MBQC rather than QC. Okay, so well, this was not work that I was a part of. So a measurement-based quantum computing. Okay, whoever is raising. Okay, so somebody is raising their hands. Let me briefly enable the chat again, I suppose. Yeah, please type your question. So because we still have some time on the break. Where was I? Yeah, so the work that was done was mostly theoretical. So I do not actually remember what the work was. So maybe, I don't know, I'll find out more about it and post it on the group. Or since I've actually spoken to you, Anurag, I'll maybe share it with you at a later stage. So yeah, one new message. I'm disabling the chat once more. I suppose whoever raised his hand has asked the question. So yeah. Oracle is a consolidated execution component built into a quantum circuit. No, it is not. As I've mentioned here, every element in my quantum circuit is a unitary transformation. It is a set of signals. My quantum computer is actually my network of qubits. It is the memory. So any unitary transformation I define is not a component, it is a set of signals. Any transformation, be it a Boolean oracle, be it some kind of a specialized gate, be it the quantum Fourier transform, whatever we are talking about, any operation that is being performed is a set of signals. It actually does not have a physical structure. So yeah, oracles and C0, I'll touch upon it. The JOSA algorithm extension, Abhishek will touch on it. I will talk about it. So now I will explain the Deutsch algorithm from stages S3 onwards. And then I will talk about the C0 gate oracles. So we have 2.5 minutes to go. Let me start a new share. That is, yeah. Yeah, so, oops. Yeah, so stage 3. So I suppose you've followed that the state here would be plus tensor minus. So at this point, since the minus is being passed into the target as defined before, this will make my bit oracle that is presented here into a face oracle. So the minus state will go as itself, whereas a whole face factor corresponding to the output of the function is acquired. So the input state here is 0 minus plus 1 minus whole divided by root 2. When UF is applied on that, I will get minus 1 to the power F0, 0 minus plus minus 1 to the power F1, 1 minus. I'm factoring the minus out entirely. So I'm writing this state as 1 over root 2 minus 1 to the power F0 ket 0 plus minus 1 to the power F1 ket 1 tensored entirely with ket minus. So in this case, if F0 is equal to F1, then this signs are common. They can be pulled out and neglected as a global phase factor. If F0 is not equal to F1, then there is a relative minus sign. It is either minus 0 plus 1 or plus 0 minus 1. So the state is either minus ket minus or ket minus. So after that, we apply the Hadamard operation. So if it is, sorry, the state is either ket plus or minus ket minus. Sorry, I'm really sorry. So when F0 is equal to F1, the state after S3 is plus minus, in which case applying a Hadamard transformation on the first qubit gives me 0. When F0 is not equal to F1, I will get the minus state on the first qubit, and applying a Hadamard transformation will give me the state 1. And therefore, by measuring the first qubit with respect to the computational basis, I can tell definitively whether the given oracle corresponds to a a constant function or a balanced function. So now let me quickly go to the C0 oracles. Yeah, 1 minute and I shall be done. So yeah, so remembering the properties of the C0 gate, if this qubit is 1, then the output will be 1 1. If this qubit is 0, then the output will be 0 0. This initial state is fixed at 0. Therefore, this implements the Boolean function f of x equal to x. In this case, I have applied no circuit at all. So this is actually a trivial representation. So this is an oracle only in the sense of the definition. So if somebody sees this circuit, they will obviously know that this state remains a constant. So that is exactly why I'm saying this is the representation of a constant Boolean function. So what I have here is the input, which can be 0 or 1, but regardless of whatever my input is, this is the qubit I recognize as my output qubit. It will always be 0. So this corresponds to the Boolean function f of x equal to 0. In this case, similarly, it corresponds to f of x equal to 1. Over here, since I know this corresponds to f of x equal to x, after evaluating that, I'm applying a further x gate, which will invert that. Therefore, if x was 1 here, I will have a 1 as it enters here. If I put a slice over here, a stage over here, and therefore it will become 0. If it was 0 here, it will get reinverted and I will get 1. So this corresponds to the single bit Boolean function f of x equal to x bar. So yeah, I guess with that, I'm done for today.